So let's review the electrolytic cell expanding problems. Expanding because they're getting a little more difficult, but they're based on the same principles. So what do we have here? They gave us a standard reduction potential table, an abridged version, because you're not going to get the full version on the test, a real test, but hey, you do so for me on tests. And what they say, we have a fuel cell, electrolysis of water. We've seen this before. And it produced 0.36 grams of oxygen gas and 0.45 grams of hydrogen. We're making the pure form. And that's what's happening below here. So if we kind of come down here, we're making hydrogen gas and we're making oxygen gas. If we did a demonstration in class and reviewed this, you'd recognize this very well. And so what's happening here is water, and two of them are being decomposed with energy to make what? Hydrogen, and two of those, and one oxygen. And we know that to be true because there's twice as much hydrogen gas. Okay, so this is something we've seen before. And again, I introduced this in class, but in any case, you're going to live and die by the reduction potential tables. So given those grams, and they also gave me voltage, I'm sorry, they gave me the amperage, which is going to be helpful in other questions on the back side if you flip that over 9 times or 3 times. But right now, let's connect the electrical leads to correctly produce the correct gas in an electrolytic cell. Now, what they said here, or what I said here, because it is my problem, is I want to produce the correct gas. So again, as you guys know, you could make this electrolytic cell the cathode or the anode depending upon how you label it or how you connect it to a battery. So because I'm telling you we're producing hydrogen gas, we have to connect our voltaic cell to correctly to make the right reaction occur. So we should see that this is the voltaic cell here. The salt bridge gives it away. All right, and we see that we're producing this reaction by the forcing of this reaction by the energy provided. Anytime there's an electrolytic cell, okay, you must have an energy source because they're always going to be, of course, non-spontaneous. So the first thing I want to do is connect the electrical leads correctly to produce the correct gas. So that being stated, let's look at the hydrogen gas being produced on the right. If I look at my net potential tables, I see that I am producing hydrogen gas if water gains electrons. Gaining electrons. So my friends, in chemistry, this is the reduction half reaction as written, okay, that we're getting from this little table. So if this is the reduction reaction, I know that red cat reduction always occurs at the cathode. So I'm going to write this. This electrode here is the cathode. Okay, now this must be the anode, but just to make sure, and it must be logical to you, the anode is always the place of oxidation. So what is oxidizing? Well, water is. And so water, okay, must be shooting water out. Now remember, this is the standard reduction potential tables. So therefore, everything's written as reduction. So I'm looking for something to go the other way, and there's water going the other way. And so if it's going the other way, it's really good at getting made this way. Its spontaneity is really good. Its entropy in the universe is increasing. It's terrible going the other way. So we're going to have to go the other way here. So what's happening is we're going to be making oxygen, hey, by water, what? Oxidizing, going in the reverse way here. And so that makes sense that the anode would produce oxygen because water is going to get oxidized. So let's go write those reactions. So the cathode is the place of reduction. Red cat is the mnemonic we use. So the reduction half reaction as written is going to be two H2Os plus the 2 electrons that are absorbed. It's called reduction, gaining these electrons. And we're going to make the hydrogen gas that's collected in the top of that. And of course, 2 hydroxides. And we talked about this reaction in class. Okay, now the oxidation half reactions, we're producing oxygen so that water, okay, is going to get what? It's going to get oxidized. So we're going to have to go the other way. So we're going to have what? 2 water molecules Okay, going the opposite way is going to make the O2. It's going to be plus 4 protons, 4 H pluses. Each H plus is a proton. Hydrogen without an electron is a single proton because it has no neutrons. And then 4 electrons are given up. Okay, and don't get crazy, both what? Water is in the same side of the reaction. Now why? Because it's both getting oxidized and getting oxidized and reduced. Now, before we can cancel our hearts away and get an overall reaction, we're going to have to make sure that the electrons are balanced in my half reaction, and they are not. So by the distributive property, I'm going to multiply the top reaction by 2. This is going to give me 4, or as we say in Riverhead, foe, and this is going to give me 4 here. This is going to give me, remember, I'm multiplying by 2 all the way through. All right, and I do that because it's going to give me the 4 electrons, and I need that to cancel. Now, once I have the 4 electrons on this side, the 4 electrons on this side, I know that I can add these guys together. So what I'm going to get is an overall reaction is 4 plus 2 is 6 water molecules. I'm getting crazy. All right. Gets broken down into, add these up. Okay, well, there's 2 hydrogens. There's no other hydrogen, so it's going to be 2 H2s. It's going to be an oxygen molecule. And we're going to have 4 H pluses. And what? 2 and I'm sorry, I forgot here. This was 2 hydroxides originally. This should be 4 hydroxides. And you say, oh, Mr. Grodsky, what are you doing? Because I made a mistake. All right. And you can clearly see in the reduction half reaction, okay, I have 2 here, and I should have had a 2 there originally. And so when I multiplied everything by 2, by the distributive property, this would become 4. So some people are probably screaming at me, oh, you earlier. So that's why that should be 4. Okay, and hey, sometimes you'll fix your mistakes and we learn from them. All right, moving forward. So we're putting them together. So yes, there was 2 H's. Okay, notice there was only an H2 there, but there was 2 there. I should have had that originally. I feel bad, and now I'm over it. Okay, now some people, okay, want to combine an H plus. Okay, we haven't done acid and base yet, so some people want to combine this into water, 4 water molecules, but that's we're not going to do that. We're just going to leave it that right there for now, and we'll pick that up another time. Now let's do net potentials, because we know what's oxidizing and what's reducing now. And so since we know what is reducing, okay, on the reduction side, all right, we know that this was negative 0.83 volts. Hey, and who was the positive? Well, that's kind of a trick question. There was no positive because we're going in the opposite direction for water getting what? Oxidized. So we've got to flip that sign. So that's also negative 1 point. It's also negative 1.23. Put them together and you get, that goes to 6, that goes to a 1, and that's a 0, and you get negative 2.06. Okay, important for the negative sign, and it's also important that you put down the unit, the volt. Okay, so there you go. Make sure you flip the sign for the oxidation half cell. Why? Because it's written as reduction. All right, moving forward. And electrochemical cell. All right, well, the first step before I can even think about connecting these to make this side the cathode, I got to figure out who the anode is. So I've got chromium and I've got gold. Well, I know gold's bad at oxidizing, but if I forget, I go to my standard reduction potential tables. And as I can see, chromium, when it oxidizes, goes this way. It's going to be what? Positive 0.74 volts. And when gold goes this way, it's going to be negative 1.5. Who's better at oxidizing? Chromium. So party people, I know that chromium is my anode. And this is my cathode. And what happens at the anode? Oxidation. Well, let's do reduction first. So in the solution, we should see that that is Au plus 3, right? Because each nitrate is -1. We've seen that many times over. We should be getting used to it. Au plus 3, hey, that's going to become what? That's going to become solid gold, so it's going to gain 3 electrons. Gaining electrons is reduction because your charge goes down. We've seen this before. Imagine that, plating. Ions becoming solid occur at the cathode. And at the anode, we have chromium 0, okay, giving off how many electrons? Well, in solution, we've got chromium plus 3. So that kind of clues us in that a piece of solid chromium, okay, is going to become chromium plus 3 and give off 3 electrons. Very nice that I gave you half reactions that have the what? Have the same electrons being absorbed in reduction as produced as oxidation. You can cancel your hearts away, and the overall reaction is Au plus 3 plus chromium 0 gives me Au0 plus chromium plus 3. The overall net potential, okay, we're going to have to go and look at my volts. We're going to write down the one who is reducing, and that is the Au plus 3, because our standard reduction table is always written as reduction. So as written, I have my, and I know I have things written over it, so let's kind of get rid of that. As written, it's going to be positive 1.50. Okay, so I'm going to write that there. So as written, it's 1.50 volts. It's positive. Au plus 3 loves to reduce because gold solid hates to oxidize. Really good at one way, you're terrible at the other. Hoping you're hearing my voice in your head with these things now. So chromium plus 3 is going to reduce. This one's going opposite. Chromium, okay, is going to oxidize. It's going to go this way. So it's going to be positive 0.74. We're going to flip this sign because it's going in the reverse. So positive 0.74 here. So positive 0.74 volts. Add them together, and you get 75 is 12. And this is 2.24. And it's volts, and it's positive. Write it in loud and proud to make sure. Okay, now we haven't connected these yet, so let's do that. So now that I know who my anode is and who my cathode is, I'm going to connect these wires. So I'm going to connect the anode, and it has to go to the cathode. Oh, I switched it on you. Wasn't the same side. All right, and the anode in the battery is negative by convention because electrons are traveling from it. And the cathode in the electrolytic cell has to be also negative because it's the battery who's making it negative. It's sending where? Sending what? It's sending electrons from the anode to the cathode. These little electrons here. So this is making this negative. And what else do we have? We have the anode on this side has to be connected to this cathode. Why? Because electrons flow from the what? From the anode to the cathode. And because this is positively charged, the cathode, it makes the anode positive. Don't just think you're just going to connect them because they're on the same side. It won't work. Anode cannot connect to the anode. Electrons flow this way. The reason why this is positive is because electrons are being pulled away from it. That's important. Okay, and there you have it all labeled. Now the last question is kind of one we had in a form that I had, so you're getting used to this. Based on the calculated net potentials for each electrochemical cell, don't fall in love. Electrochemical cells could be voltaic or electrolytic. Okay, can the voltaic cell power the electrolytic? Well, it's positive 0.24 volts here. That's the spontaneous side. And this is negative 2.06. So there is enough positive volts to drive this forward. So that would be a yes. Okay, we've seen that before. Cool beans if beans are chilled. All right, so let's go on to some more electrolytic type of calculations that people are starting to really love here. Okay, approximately, looks like I misspelled that. I feel bad, but now I'm over it. All right, I'm 2 mistakes away from being perfect. Number 8, approximately how many minutes, they're looking for time, are needed to produce the grams of oxygen gas in this fuel cell experimental apparatus. Okay, so we're looking for time. Now, if you remember back in the original problem, or at least the original statement of the problem, what are they giving me? They gave me, if you remember, they gave me the amperage, which is coulombs per second, and they gave me the amount of grams of hydrogen and oxygen. So let's go back to the question and see if we can think this through. We've been through these before, but I'm making you think about these a little bit differently. So they don't know how much time does it take to produce the grams of oxygen. Now, how many grams of oxygen was written? Well, it was 30.36 grams. So I'm going to write that in, 0.36 grams. And that was the grams of oxygen made at the what? Where was the oxygen made? It doesn't really matter, but hey, we're connecting this, made it at the anode where oxidation occurs. It's where water was oxidized. Okay. We're going to need that half reaction at some point. But some people get lost and say, how do I start this? I know I need to use Coulomb's law. I know I have to use Faraday's constant, and I got to use the amperage, but I don't know where to start. I always tell you got a multi-step problem. It's not what you do first, it's what you do last. What are we trying to solve for? They're looking for time. How many minutes? Now, what gives you time in everything we've studied in these types of problems? Well, the amperage, if you remember, okay, in this example, all right, was what? 12.0. And what does that mean? It's 12.0 coulombs of charge traveling along a point in the circuit every second. Hey, party people, the amperage is giving us a link to time. Wow. So the thing that we have to do last is that once we have the coulombs, okay, our total charge, we can actually get the seconds out of that using this relationship. So we can solve for second once we have coulombs. So now that I need to know total coulombs, coulombs is charge of electrons. And electrons do what? Move around. And how many electrons were needed to make, 0.36? A certain number based on its half reaction. And how many O2 molecules do we have here? It's based upon the mole concept. So the first thing I'm going to do is convert this into how many, because I want to know how many electrons passed around to get my coulombs. So the first step is get rid of my grams, and I know that from my periodic table, each oxygen is 16, so each of these particles is 32 grams. Right? Because if each particle of O2 is 16 and they're both bonded together, the total molecular mass is 32 grams per 1 mole. Don't get lost in the sauce. A mole just represents how many. And so I've converted a how heavy number, grams, into a how many. But I want how many what? Coulombs of charge passed around. This is what I'm going to do last. How many oxygens were made don't help me, but I do know this was a redox reaction, and there was a certain number of electrons that were used up to make the O2. So where is that? Okay, to make the O2, okay, where are we? Okay, we're making the O2. And how many electrons were involved? Okay, 4. Okay, now if you don't see that, okay, look at the original reaction. Okay, look at here. To make O2, 4 electrons had to travel around or get pulled away from that electrode to close the circuit. So every one there's 4. So it's important that now I have moles of O2. I have a how many number, and now I can use that ratio of how many. For every what? 1 O2 molecule, there was what? 4 electrons from my half reaction. I cancel away my oxygens, and what do I have? I have moles of electrons. What does that mean? How many electrons? So let's take a step back. This is how many O2 molecules. What is this? Let me go blue here. This is how many what? Electrons. This is how many or moles of electrons. Great, but what am I looking for? I want coulombs. So do I have a standard by which I can convert how many electrons. Yep, and that, my friends, is Faraday's constant, fancy F. Now, we've been writing it different ways, but I want to get rid of what? I have moles of electrons, so my electron's going to go here. And I know that for every 1 mole of electrons, there is 96,500 coulombs. Hello, we're solving for coulombs. My mole cancels. My electrons cancel, and what did I just solve for right here? Okay, if I can write it, this entire expression is the total number of coulombs. Okay, so that's what I needed to get to. Oop, it's a big B there. All right, so I got coulombs. Now, to get the time, okay, I'm going to use the amperage, right? And what's the amperage? It's the coulombs per second. But Mr. Grodsky, I got coulombs on top, so there's going to be 12 coulombs for every second. Notice I flipped it because I am going to cancel out my coulombs. I'm going to use my what? I always use my units here. Now, they didn't ask for seconds, they asked for what? Minutes. So last thing I'm going to do, party people, is there's 60 what? Seconds in every 1 minute. And we can see that seconds cancel. I'm letting my units determine that. So what's this entire expression now? It's the time. It really is helpful to know what you're doing last to figure out what you're doing first. So 0.36 divide by 32 times 4, okay, times 96,500 divide by 12 divide by 60. All right, and I get 6.03. What's left standing? Minutes. You put seconds, you get it wrong. And of course, we started with, I think it was 2 sig figs, so I'm probably good if I was to report 6.0 minutes. Okay. This 03 I'm not really sure about, but in the actual AP they give you plus or minus 1, so we're within a standard. So there is your answer right there. Again, you have to think about it, but you have to know what you're doing what. What am I doing last? Solving for a second. What type of piece of information keys me on a second? The amperage. All right, so let's go on to the last part of this, which I think is a more straightforward equation or question. How many grams of H2 gas would be produced if we ran for 10 minutes? Well, I know that amperage is 12.0 coulombs per second. That didn't change. All right, and so we're looking for the new value of hydrogen gas. So if we had that electrolytic cell running, so they're looking for grams of hydrogen gas. I'm going to produce hydrogen gas, which is made by what? It doing what? Well, if you go back to the problem, hydrogen gas is made by what? Which half reaction? Hydrogen gas is made by water getting reduced. And guess what? There are 2 electrons for every 1 H2. Ooh, there's a tie in there. So when I think about this problem, what am I doing last? I'm finding how much what? I'm finding how much H2 gas. And I'm getting grams. But then, wait a minute, to get to grams, I have to have a how many number, mole of H2. And what's the relationship between how many H2, and remember this is about electrons. Isn't there something about electrons here? Ooh, yeah. And how did we get electrons? Well, didn't we have to figure out how much coulombs were traveling? Oh, that's where we use the amperage, which has a time factor, and that's where we start the time. So this question is in reverse. Okay, again, what do we do last? We're trying to find how many grams of H2 gas. Well, how many grams of H2 gas is tied to how many H2s, which is tied to how many electrons, which is tied to the total coulombs of charge based upon the amperage. So here we go. I'm going to start with my time, 10 minutes. And I'm going to go to seconds because I know that the coulombs is based upon seconds. For every 1 minute, I've got what? 60 seconds. And minutes go bye-bye. I don't care what this number is, but I got total seconds. And now I'm going to get rid of seconds to get coulombs. That's what this is about. It's always about the flow of electrons. And so the amperage in the problem is still 12. And for every 1 second, we've got 12.0 coulombs. I've got total coulombs here. Great. Okay. But how many electrons is that? Because once I know number of electrons, I can get the how many H2s by the ratio of electrons to hydrogen in the half reaction. So now I'm going to use Faraday's constant to convert my coulombs to how many electrons. But this is going to be 96,500 coulombs on the bottom because now I'm getting rid of coulombs. And for every 1 mole of electrons, a how many number. So now this entire expression is how many what? How many electrons. Next step, let's go find how many H2s. That's what this is about. And what's the ratio? Well, isn't there 2 electrons per 1 H2? And again, if you don't know, take yourself to the half reactions. Okay? And so to produce H for every one of these, 2 electrons was absorbed by the water. Yeah, go right to the information given to you. Okay? And so what does this give me? Electrons cancel, and I'm left with what? Mole of H2. How many H2s? They didn't ask that. They asked for grams. So we know that a mole of H2 equals some number of grams. Okay, we'll get rid of the mole. 1 mole is equal to how many grams? Well, each H is 1 gram per mole. Each particle has 2 of them, so it's 2 grams. That's the molecular mass. Mole is canceled. The only unit left standing is grams of hydrogen. And let's put this through our handy dandy calculator. All right, so I saw some people in lab today trying to do these individual what? They're trying to do the reaction individually, trying to say, okay, let me go find this first, then go find this first, and they're writing stuff down, and they don't know what they're doing. They're getting lost in the sauce. Please use the dimensional analysis. Use your units. Okay, so 10 times 60, okay, times 12, divide by 1, times 1, divide by 96,500, times 1, divide by 2, and then times 2. Divide by 1 if you want to. And what you get, party people, is you get 0.0746 grams. Now we started with 3 sig fig here, 10.0 minutes, so we should have 3. So the raw answer is 0.07461, and that's grams of H2. How do I know it's grams of H2? It's the unit left standing, the descriptors left standing. And I want to round that to 3 sig figs. Remember, the leading zeros are never significant. So I look at the first 3. This one isn't greater than 5, so it stays 0.0746 grams of H2. That's how many grams of H2 we produce. Okay, and I hope that helped. I know practice. I've given you a bunch of these different types of problems, and you will see it in a surprise quiz soon. I mean, I guess it will be a surprise. Hope that helped. All right, see you later.